Okay, and we are live. All right. Welcome everyone to another meme lecture. I am Art, your wonderful host, and today we're going to talk about some common PDE solution techniques that are the integral transform methods and then the Sturm Liouville problems. And I'm going to have a scheduled crash out towards the end of the video regarding a video I saw that was very pertinent to this topic, so I figured I'd give my take on that because I thought it was dumb and pertinent. Anywho, let's get on with it then. So a transform method is what we're going to talk about first. And why do we care about transform methods? They basically are a way to solve differential equations by taking the problem, turning it into a new problem, solving that easier problem, and then taking that easy solution and then turning it back into a hard solution. Now, it basically is a long way around to get an answer in an easy fashion. Now, generically, a transform function is some sort of integral. It takes one function in and it spits out another function. It is usually a linear operator of some form, though you can sometimes get nonlinear transforms. And what happens basically is that this function k, which is called a kernel, basically acts like a matrix, right? If you think about a matrix as sort of a graveyard of numbers, as some people like to say, that graveyard of numbers represents what happens when you take one basis vector and what the output in another basis vector is going to be, right? Each entry in the matrix basically takes in one basis, spits out another basis, and it basically goes from vector to vector. And that's what this kernel does as well. If anyone watched my recent video about the Chinese population models, what can happen is you can use a similar idea basically to say, you can take a whole population of women and basically take an integral on that and spit out a single number to estimate the birth rate. It's a similar idea there. Now the kernel there basically is more of just a linear form that basically takes a whole function and reduces it down to a single number, whereas this one is a map from functions to functions. So there are many special kernels. Ones that are particularly nice are symmetric kernels. That basically means if you swap the arguments around, they are still equal. Most kernels will also have an inverse kernel, that if you apply that inverse transform to the original transform, you'll get your original function back. And this is an important step because if you want to actually solve a problem and get a real answer in the real world, you're going to have to make that step. However, even if you can't make that step or it's very hard to make that step, even still getting an analysis on the far side, this transform side, it can usually still lend some insight to a problem. Now here I've listed off a few famous integral transforms. The most famous is probably the Fourier transform, which I have defined here as e to the negative ist over the square root of 2 pi. Now there are a number of different definitions for the Fourier transform. Some have a 2 pi on the inverse factor, others have the 2 pi up in the integral term. I use this one because it and its inverse are essentially the same up to that minus sign in the exponent. Another famous transform is the Hilbert transform. What it is it's an integral kernel of a reciprocal function. It is equal to its inverse is the negative of itself. And so if you can compute a Hilbert transform, it's very easy to compute its inverse. And finally, we have the Laplace transform. And the Laplace transform basically is e to the negative st. And its inverse is e to the st over 2 pi. And again, that 2 pi is a similar 2 pi as that one that shows up in the Fourier transform and that pi that shows up in the Hilbert transform. They're all, in this case, all three of them do sort of have, they all have similar, they all sort of speak to each other. That pi is sort of hidden in there for common reasons, basically. That's a normalization factor to control the scale basically within the map. And so whenever you have something like that, a pi is going to show up oftentimes. All right, so we'll consider a very basic example of an integral transform by the Laplace transform. And what we have here is we have a forced oscillator equation. So we have a second derivative plus its original function is equal to some Dirac delta at a time a. There are no initial conditions, so essentially what we have here is an oscillator that gets a force at a specific moment in time, and we're trying to calculate basically the response to that forcing. So what we can do is we can compute the Laplace transform for a derivative. Now, if you have a function, its if you know the Laplace transform for some function, the derivative of that function will have a similar Laplace transform with a power of s in front of it, with some additional terms for initial conditions, but here the initial conditions are both 0, so that's fine. And then the Laplace transform for a delta function, because it is an integral kernel, it basically takes, you basically say, hey, you basically evaluate the kernel at the time t equals a, and s remains fixed. So if you apply that into this equation, you basically get an equation in f hat, and if you solve for that, it's the rightmost one that is correct. F hat is equal to e to the negative as over 1 plus s squared. I forget what I originally had as a forcing function, but I figured this one was more interesting. Anywho, one is probably the forcing at time 0. That's probably where that came from anyhow. So we can take the inverse Laplace transform of that, and essentially what happens though is using the rules of Laplace transforms, you can actually get out a fairly easy answer of theta of t minus a times sine of t minus a, where theta is the Heaviside step function, so it's 0 before a and then 1 after a. And what we get basically is nothing is happening, and then suddenly it's oscillating with frequency 1, which is what you expect given the frequency of this particular oscillator. And what happened is that this differential equation in t is turned into a much simpler algebraic equation in s. Right? And that's what makes it so much easier to solve, right? Differential equations, they're difficult, right? You know, you have to make all sorts of ansatz and guesses and stuff like that, or you might have to do separation of variables. But if you can turn it into an integral transform instead of having to deal with derivatives or a lot of derivatives, you can reduce it down to a much simpler algebraic equation often, or just even a simpler equation, as we'll see in our next example, the area equation. Now, the area equation is a very interesting equation in that it's the second derivative is dependent on the value of the function and the time, but the sign of that time, right, it switches. So f double prime is equal to the time times the function. And that's an interesting twist, right? So what basically happens is that before t equals 0, so when t is negative, it's going to oscillate around. But then what happens when t when t is greater than 0, it'll start behaving more like an exponential function. And and the area equation will actually show that. But if we want to solve it, we have to apply we're going to apply the Fourier transform. Now, the Fourier transform has a very similar rule as before, where derivatives become powers and powers become derivatives. So the derivative becomes that power s squared of f that we see in the second term, and then that t term becomes a derivative with respect to s. And so what this equation becomes is, instead of it being a second order differential equation in t, it is now a first order differential equation in s. And a first order differential equation is easier to solve than a second order differential equation. A little bit of algebra and a little bit of exponentiation later, we can then solve for f hat. And f hat is going to be some constant times an exponential, a cubic imaginary exponential. And that is used then to define what the area function is. Basically takes that exponential function and applies the inverse Fourier transform. One of the definitions of the area function is this integral, this AI integral, where basically we have that coefficient of pi out front from the inverse Fourier transform, and we see cosine of s cubed plus ts. Now that ts is that e to the I ts that is typical of the inverse Fourier transform, and then that s cubed is basically coming out from the Fourier transform function that we have. And the reason though it's cosine is because we're taking a real component out of it, basically. Right? We have an imaginary exponential We're turning it real. We apply that real. We find that real component, and what we get out of it is some sort of cosine function, and that's what we're seeing here. There's a secondary function that, if I recall correctly, deals with sort of the exponential side of the solutions, if my memory serves me correctly. Anyway, you can also apply these ideas to PDEs in multiple dimensions, and you can apply different transforms to different dimensions. So in this example, we have a forced wave equation with some impulse I, some initial conditions G and H. And so if you apply the Laplace transform in the time direction to that equation, you get this nice, long, complicated equation in terms of X and S, right? But this is still a differential equation of some difficulty. So then we can also then apply a Fourier transform in X to get a significantly simpler algebraic equation in the KS space, right? And then what you can do is you can do a little bit of manipulation to find that the F hat is basically going to be a weighted sum of the impulse and the initial conditions, scaled appropriately by S's and K's. Now let's take a moment to recognize this lowest part here. We have S squared, that's like the frequency, that's in frequency space, or not frequency space, but it has units of inverse time plus a speed times inverse units. Right, so all those units of S squared plus C squared K squared will have units of inverse time squared. And we'll just keep that in mind as we continue. So if we then invert it, we're going to have to we often have some complicated integral to do. And this is the integral we're going to have to solve if we want to find f of x and t, right? And so we have an inverse Fourier transform and an inverse Laplace transform. We see these different limits of integration showing up for the k and the inverse of s. We have all these different functions showing up. And what we notice, though, is that in S, and to some degree, and hit very explicitly in S and implicitly in K, what happens is we have to perform an integration around the simple poles. And simple poles, if you have not taken complex analysis, is basically a function that takes the form 1 over x, or 1 over z minus a. Right? It's basically a reciprocal linear function. Right? So you take some linear function and you invert it, basically. It's a term of x to the negative 1, z to the negative 1. And basically, there's a very famous result in complex analysis called Cauchy's theorem. Basically, it says that all the other powers in a function's Taylor series or a function's Laurent series don't matter to the calculation of an integral. It's only those terms that matter, and those are called the residues. And essentially, what happens is these residues become key in performing all these calculations. Now, what we'll find is that the poles for this problem occur when k is equal to plus or minus ICS. And so that first integral is going to reduce to the cases where basically we say, hey, k is equal to plus or minus ICS. And you see in that second equation, f of x t I, where we still need to do the inverse Laplace transform, we have f of s times e to the s t plus or minus x minus c. Now what that denotes is that there are two terms in here. One of the form e to the st plus xc, and one of the form e to the st minus xc. Right, there's two different terms, but I just combined them into one for notational convenience. And then if you do a Fourier, an inverse Laplace transform on that, you're going to get out two functions. One of the form f of t plus x over c, and one of the form f of t minus xc. And what that indicates is that there are, basically what happens is that all the solution to this equation is going to travel in two different directions with speed c. So the equation, right, wherever t plus x over c is equal to some constant, the function is going to travel along those lines. And those lines are called characteristics. And this And these poles can tell us, and more broadly speaking, though, we're not always going to have super nice, clean characteristics, but they can tell us, so the poles of integrals like this are going to give us properties of the solutions, even without full explicit calculations. Basically, the most common way for this to happen is you can apply a Fourier transform in both time and in space, right? From t to omega and from x to k. And the poles of the resulting Fourier transform are going to satisfy what is called a dispersion relation. It's basically a relation, not an equation, that says, okay, if we have a solution at frequency omega, it's going to have some response at wave number k. Or if we have something happening at wave number k, it is going to respond at frequency omega. And there are different quantities, sort of subquantities, like omega over k and the derivative of omega with respect to k, that calculate velocities of this. And so if you've ever heard, and I have this little note, speed of light. So if you've ever heard of things traveling faster than the speed of light, what they are likely referring to is they are likely referring to some sort of wave where omega over k exceeds that speed of light. And that's okay because not to go too deep into the weeds of waves at this stage, but omega over k is basically talking about, what it basically talks about is how fast something is oscillating sort of in a local sense. It's basically a bunch of ripples. Basically, it's talking about the ripples. Nothing is really moving. Whereas the group velocity, that derivative of omega with respect to t, that talks about basically the bulk of the energy. How is that energy moving from one space to another? Or how is this mass moving from one place to another? And it is that quantity that cannot exceed the speed of light in a normal circumstance. Now, the dispersion relation also gives us a hint at the classification of partial differential equations. When we do the Fourier transform in t and x, the poles of the result will satisfy that dispersion relation, and that can tell us things about the classification. A hyperbolic equation is one whose dispersion relation has real solutions in omega and in k. And they call it a hyperbolic equation because oftentimes the curves that result are some sort of hyperbolic shape. So the example equation I have here is the Klein-Gordon equation, where basically you have something propagating in time and space. You have something propagating in space across time with some mass m squared, and we get a equation in f hat. And if we assume that f hat is not equal to 0, the curve omega squared equals c squared k squared plus m squared, that is a hyperbolic curve in omega and in c. Right? And that hyperbola shape is in large part why we call the equations of that type a hyperbolic equation. Now, in a similar fashion, an elliptic equation has no real roots. And so here we have it's not the, oh goodness, what is it called? It's the Poisson equation. And that Poisson equation, basically, what happens is if you apply that Fourier transform from x to k and y to l, what we'll get there is we're going to get some sort of equation in the form k squared plus l squared is equal to m squared, or negative m squared. And it's a nice elliptic circular shape, right? The variables, right? The mass serves basically as some sort of radius. And that curve in KL space that it forms is an ellipse, or in more precise terms, it is a circle. And finally, we have a parabolic equation, which I screwed up the LaTeX on. However, we have a derivative of f with respect to t minus a second derivative of f with respect to x. And applying the Fourier transform to that, we have omega equals negative iak squared, right? Now, there's that extra I, and that's a repeated root, basically, so we have a double root, which makes it parabolic. But we can also sort of see it in just right, if you look at that equation as like as a geometry problem, we're saying, oh, omega equals k squared. That's some sort of parabola. And that's another great way to think about how to name it, right? So you look at the dispersion curves, the dispersion relations, And the shape it produces sort of suggests, like, oh, what type of PDE is it? Is it hyperbolic? Is it elliptic? Is it parabolic? And the differences in all of these have huge implications in terms of solutions. Like, hyperbolic equations are usually significantly easier to solve in that we can just basically step forward through time fairly explicitly. As long as we're not worrying, as long as we're not going too fast, we can usually simulate hyperbolic equations with very little, maybe some implicit solutions, but it's typically fairly easy to solve. An elliptic equation, on the other hand, requires basically you're looking at the whole space all at once, and you're usually doing some sort of iterative solution if you're trying to solve it numerically. And a parabolic equation sort of sits on that boundary between elliptic and hyperbolic. And so it can take some advantage of being partially, having one foot in the hyperbolic pool, and then take advantage of other parts of being in the elliptic pool. It sort of straddles that boundary between the two. Now, and I've promised my explanation for a long time on these PDE classifications. So hopefully this is satisfactory to those who've been waiting on that. I think Vladify, I think he was looking for it. There might have been one other person who had asked about that as well. So hopefully that is sufficient. I'll probably talk more about this, these different PDE types over the year, as I continue making these. But anyway, so one final point I want to make about transform methods. So the Fourier transform in particular came to mind here as an example of an uncertainty principle. Right. Now, if you've taken quantum mechanics, or if you've read enough about quantum mechanics, you know that the uncertainty principle in a broad sense is about you have different observables, which are operators basically, and if the operators in question do not commute with each other, and you try to do these variance calculations on them, if they don't commute with each other, they're not going to cancel out in a nice way, resulting in a nice lower bound on it. And this is an example of that. And it's not, but this is certainly not universal, but this definitely applies to the position, momentum, and the similar energy time uncertainty that we have in that uncertainty can be expressed in terms of Fourier transforms. And in its most fundamental form, what we have is we have a function f of x, its Fourier transform f hat of k, and we have two moment integrals. Now, x squared and k squared. And what these basically do is they compute basically the spread of the function, right? If you've taken a probability class, you probably remember that the variance of some random variable x is the expectation of x squared minus the expectation of x all squared, right? But here we're assuming that the expectation value of x is equal to 0, so we can ignore that shift. We're just worried about those higher moments. And what this uncertainty principle states is that if we take that moment in x and we take that moment in k, we do the whole integral over the entire domain, we have a nice lower bound in terms of just the original function, the original L2 norm of the function all squared, with a 16 pi squared as the appropriate normalization constant. Now, in quantum mechanics, what's really nice is that L2 norm, that f of x squared integral on the right, that's always going to evaluate to 1. Also in quantum mechanics, there's usually going to be some sort of h bar that shows up for reasons of units, but I'm not worried about units. And basically what it means is that there's a minimum amount of spread between a function and its Fourier transform. Now, the first example to consider is what happens if you have a delta function. Now, a delta function, it's not really a function, we'll call it a function then. Right, a delta function exists at a single point, right? Delta of x minus a exists at the point x equals a. But if you take the Fourier transform of that, what will happen is basically you're going to get some very big exponential, and it's going to be not exponential, it's going to be like a sinusoid basically. but that sinusoid will have value 1, and it will be very broad and over the entire domain. Right? If you know what it basically says is if you compute that Fourier transform of the delta function, the density of that Fourier transform is going to be very, very spread out. Now, the minimal value of this uncertainty principle is basically going to be some sort of Gaussian. It's a nice bell curve. The bell curve, the Gaussian is an eigenfunction of the Fourier transform. And so what you can do is you can find an appropriately normalized and scaled Gaussian. You can find that and its Fourier transform, and you can actually do a little bit of juggling on it to find that critical value. I don't remember it off the top of my head, but basically it's going to be a Gaussian times another Gaussian is bounded by the norm of a Gaussian, which is, about as good as you get. So so something is here-ish, but it's sort of spread out, and you can also then say with confidence that its momentum is going to be here-ish and also spread out. And that sort of wraps up transform methods. And then another idea I want to talk about is about Sturm-Liouville theory. Now, Sturm-Liouville equations broadly take the form of this second order differential equation here, where we have functions p, q, and x are real valued functions on some closed interval of a to b of the reals. W is known as the weight function, and lambda is known as the spectral parameter. Those are probably the two most important functions in our analysis of a Sturm-Liouville equation. And these show up very broadly, right? Most of the equations we've looked at even today in this lecture are second order differential equations. And what happens basically in the process of solving PDEs is you're going to get a whole bunch of these second order differential equations, and you're going to you're going to reduce them somehow and turn them into a Sturm-Liouville problem. And that and solving these Sturm-Liouville problems has a bunch of nice properties to them that make the analysis very interesting and revelatory and allows for a lot of powerful computation to be exploited. Sturm-Liouville problems need to have some sort of appropriate boundary conditions. They need to be linear boundary conditions, homogeneous boundary conditions. So what I mean by homogeneous is that they have to equal, the weight of y and y prime has to sum up to 0. And what these do is they make this whole differential operator self-adjoint. So what does self-adjoint mean? The differential operator, L of y, we can define in terms of p, the derivative, and q. It is self-adjoint under the inner product defined with respect to the weight. And what that does basically is that ensures that the spectral parameter, the eigenvalue as it's called, is going to be real, and it ensures the orthogonality of the eigenfunction. Basically, we can move L from LF of G. The inner product of LF and G is equal to the inner product of F and LG. That's essentially what happens with self-adjointness. If you've taken linear algebra, a self-adjoint operator is much like a symmetric matrix. And if you use that matrix to build out some sort of inner product, you know that if you have a symmetric matrix, the inner product of AX and Y is the same as the inner product of X and AY. Same idea, just higher dimensional. And in that case, you can reduce this whole thing to an eigenvalue problem in function space, though. You have a nice, you have a linear operator and then a spectral parameter with that weight function W and Y. And the key result in Sturm-Liouville theory are the following facts. So you're going to have a discrete set of eigenvalues of lambda 1, which is less than lambda 2, which is less than an infinite sequence of eigenvalues. You're going to have a sequence of associated eigenfunctions, y1, y2, etc. And those eigenfunctions are going to be orthogonal to each other with respect to that weighting function, that inner product I mentioned before. So you have one eigenfunction and the other. You take that integral with that weight function, unless they are from unless they correspond to that same eigenvalue, they are going to be orthogonal. And this is very nice for us. That orthogonality basically allows us to build out a basis for any L2 function with this weight space. So if some function is L2 with respect to that weight over that domain, you can expand it out using this spectral series, basically. And you can compute the coefficients in that basis using a pair of inner products. So you take your function f, you map it, or you take an inner product with the appropriate eigenfunction, and then you normalize by the norm of that eigenfunction. Now, if you're smart about that, you'll have the eigenfunction defined so it will always have weight 1, so you don't have to compute that denominator. But broadly speaking, this is what you do. And this is much like projection, right? If you recall from linear algebra, when you project one vector onto another, you take u dot v, and then you divide by the vector v squared if you're projecting u onto v. And then if you have a whole sequence of these v's that you're projecting onto, and those v's are all orthogonal, that vector u is a weighted sum of those vectors v that you compute via this projection. It's the same idea as that, just higher dimension, right? And that's a key idea of a lot of this. You take the stuff you know from basic linear algebra, you carry it over to a higher dimensional function space. Now, there's a lot of topology you have to be concerned about in terms of like, oh, function spaces are infinite dimensional. There are hiccups about like, oh, measure spaces and continuity and stuff like that. And those are certainly all important. But philosophically, in terms of understanding the fundamental idea of it, basically take linear algebra and beef it up. Some examples of Sturm-Liouville problems and their associated functions. These are a lot of functions that you've probably heard of. If you've ever heard of the Legendre problem, that's going to be a sequence of polynomials. It solves the Legendre-Sturm-Liouville problem with weight 1, P1. Likewise, you're going to have the Fourier series. Fourier series is basically another basis for the same weighting. And then you'll have Bessel functions. And Bessel functions are also of a very similar type. You have basically a derivative of x times another derivative, basically. Generally speaking, you could take any Sturm-Liouville equation and you can actually reduce it down using a fancy substitution into an equation of the form second derivative of psi with respect to z is equal to lambda minus vz of psi. I'll say that 5 times fast. Don't actually, but... and this is analogous to a time-independent Schrodinger equation, and basically, if you know anything about a Schrodinger equation and its solutions, so basically those sort of quanta that you see in any sort of quantum mechanical problem, right? That quanta is a quantization, and that quantization comes from the fact that you can reduce a lot of these problems to these discretized solutions. So the discrete hydrogen orbitals, the discrete states of a quantum harmonic oscillator, all of those come back down to the fact that the equations that describe quantum mechanics are of a Sturm-Liouville form, and since they are of a Sturm-Liouville form, you're going to get this discrete spectrum out of it. Obviously, if you're dealing with a more free, if you're dealing with a free quantum particle, well, then you're going to have a much broader, you're not going to get that nice discrete spectrum. You're going to get like a whole range of wave numbers and frequencies and stuff like that, and take some quantum field theory or advanced quantum mechanics to talk about that. But you don't have to worry about a second quantization or something like that. But for very basic quantum mechanics, where there's a nice closed up system, you can reduce it all to Sturm-Liouville problems. Some other fun notes is that basis set is going to be complete. I think I mentioned that before. The series converges in a mean square sense. It basically converges in that L2 sense. And broadly speaking, though, however, if you have such a series, if you have such an orthogonal basis, you may or may not get pointwise convergence. If you're familiar with the idea of Gibbs phenomena, basically what happens in a Fourier series is if you have some discontinuous function, the sines and cosines that are used to construct a Fourier series are all smooth and continuous. And so if you have a discontinuous function, what you're going to get at the discontinuity is you're going to get some very big and spurious oscillations showing up that you really can't avoid if you're using some sort of spectral method. These methods are very useful in PDEs because essentially what happens when you solve these PDEs is you use what's called a separation of variables. And that separation of variables basically breaks up the problem into several Sturm-Liouville problems, one for each dimension. So you'll have a Sturm-Liouville problem in time, one for the x dimension, one for a y dimension, one for a z dimension if you have it. And in summary, though, Sturm-Liouville problems basically connect these different differential operators, the orthogonality, or an orthogonal basis, and this eigenvalue problem together under all one nice umbrella. It allows a lot of functions to be broken down in several different ways, and it allows us to solve some very important PDEs, right? So one example that I want to talk about as far as solving a PDE using a orthogonal basis like this is a plate theory, right? So if you've ever taken some salt or something like that and you put it on a vibrating plate of some sort, you're going to get and you oscillate it at a certain frequency, you'll get these nice little standing wave patterns. Let me cut over to another screen to show you this. Oh yeah, we'll get to her in a second. But if you have, so this Wikipedia page talks about vibrations of plates. So if you've ever taken a bunch of salt on a vibrating plate, you might get a shape that looks something like this. And really what that shape is it's a solution to these problems that are basically some very complicated Sturm-Liouville problems, right? If you see here, we have this, we have that sort of form, that dr, r, dr, right? There's that fundamental Sturm-Liouville form showing up there. Now, these are biharmonic equations, so we sort of have a doubled Sturm-Liouville operator being applied there, but it's still fundamentally, it's the same idea in practice, just generalized to a crazier degree. And you get these nice little discrete modes showing up, right? So you get this one that oscillates sort of centrally, and then we get this sort of Mexican hat, sombrero oscillation. If you have rectangular plates, you basically break it down. You can count sort of like, oh, this is the two form mode because, oh, it has two antinodes in one direction and then four antinodes in another direction. Right. And, these discrete modes come out of a Sturm-Liouville problem, right? As I've been asserting the whole time. And this is all good, right? This is all good and legitimate math. However, though, people have a tendency to take, good and legitimate math, like Sturm-Liouville problems, and like I mentioned before, the Heisenberg uncertainty principle, and they start saying all sorts of crazy, batshit insane things like, oh, you can use these ideas and vibrations to, unlock your mind or something like that. So I want to show this. I want to watch this video and sort of have a crash out on this. So here we go.
How to manipulate reality. The Vikings knew how to manipulate reality through sound, and we're finally learning that they were right.
Okay, the Vikings manipulate reality through sound. That sounds like they're assuming that the Vikings were basically the Nords of Skyrim, right? Oh, I'm a dragonborn, I can shout like a dragon and change reality. Like, give me a break. Sorry.
They used Galdr, a special type of chanting. If you chant the right words with the right tone, reality shifts.
Dragon shouts, I'm telling you.
Odin himself was said to have known 18 Galdr.
18?
Chants that could heal, control the elements, and even raise the dead.
Yeah, no, dragon shouts.
This stems from an even older Indo-European belief. Ancient India had Om and Nada Yoga, where the entire cosmos is vibration.
Stupid.
Tibetan monks use chanting and singing bowls to alter consciousness.
Okay, so singing bowls are fun, right? You hit them, and they emit a sound, and that sound and the frequencies you hear are basically, right? Now, a bowl is not a plate, but a bowl is governed by basically the same equations as a plate, as a solid elastic, it's close to elastic material in terms of it'll vibrate and oscillate, and it'll have modes similar to this. Obviously, because the curvature of the bowl, it's not going to be quite the same, but it'll have a spectral sequence of different frequencies being emitted, right? So that's normal, good math and science there, right? You could, if you took one and if you took a singing bowl, you slapped it, and you had a little spectrogram analysis going on there, you'd see a sequence of very nice spikes showing up. Anyway, and that comes out of that Sturm Liouville theory, right? Anyhow,
Modern science is catching up. Somatics show
this is the shot here that made me have a crash out, because I've seen these plates showing up before here. Let me see if we can show. Right, we have several discrete frequencies, so this is probably the 1-1 mode. This probably looks like a 1-3 mode, or maybe a 3-3 mode. Maybe a 2 mode. I don't know. Right, but at different frequencies, and if we look at the relations of the frequencies with each other, let's see, we have